Alright, so here we are with lesson 15, solving area problems using scale drawings. So let's do the opening exercise together. For each diagram, drawing 2 is the scale drawing of drawing 1. Complete the accompanying charts. For each drawing, identify the side lengths, determine the area, and compute the scale factor. Convert each scale factor into a fraction in percent. Examine the results and write a conclusion relating scale factors to the area. Alright, so based on our chart, if we compare side of drawing 1 to drawing 2, side 1 is 3 units and the side of drawing 2 is 9 units. So how would we write this as a scale factor? Well, again, remembering that quantity is equal to percent times the whole. Drawing 2 is our quantity and drawing 1 is our whole. So in order to plug in what we know, 9 is equal to the percent times 3. That means that we would have a scale factor of 3 over 1, or 3, and to write that as a percent would be 300%. So now let's take a look at the areas. Remember that the area is equal to length times width. So that means we would have 3 times 3 square units, which means our area of drawing 1 is 9 square units. When we do that for drawing 2, you would get 81 square units. So now, using the same quantity is equal to percent times the whole, the quantity would be drawing 2 is equal to the percent times the drawing 1 area. So 81 is equal to percent times 9. And when we get our scale factor, that would be 9 over 1, or 9, which as a percent would be 900%. So the scale factor between drawing 1 and drawing 2 is 3. And the quotient of the areas is 9. Because again, the quotient of the areas means 81 divided by 9, which gives us 9. Alright, let's take a look at drawing 1 and drawing 2, which are two circles. So based on the radius, drawing 1 is 4 units and drawing 2 is 8 units. So again, using quantity is equal to percent times the whole. Drawing 2 is equal to percent times drawing 1. So that'd be 8 equals percent times 4, which would be 2 over 1, or 200%. So now the area of a circle is area equals pi times r squared. If the radius squared is 4 squared, then that means we'd have 16 pi square units. And we're going to leave everything in terms of pi so that we don't have to deal with figuring that out, because it's going to end up canceling out here in a second anyways. So if we apply that to drawing 2, we have pi times radius squared, so that's 8 squared is 64. So area is equal to 64 pi square units. Again, applying the same quantity is equal to percent times the whole. We have the drawing 2 area is equal to percent times drawing 1 area. So 64 pi is equal to percent times 16 pi. Here's where I was talking about pi is going to end up canceling each other out. So we end up with 4 over 1, or 4, which is 400%. So the scale factor, again, if we're just talking about the radius, is 2, and then the quotient of the areas would be 4, because again, 4 over 1 is 4. Alright, how about this square? The side length drawing is 12 units, and for drawing 2 is 6 units. So, doing this one at a time, you should be able to figure out that we have 6 over 12, because again, drawing 2 is our quantity and drawing 1 is our whole. So since it's obviously a reduction, this is going to be less than 100%, so in this case it is 50%. Now if we take the area again, 12 squared is 144 square units, and 6 squared is 36 square units. So what do you think the scale factor as a percent is going to be? Well, setting it up like we've been doing for the last several problems, 36 is equal to percent times 144, and 36 divided by 104 44 is 1/4, which is 25%. So the scale factor is 1/2, and the quotient of the areas is 1/4. So based on all of these exercises, what is our conclusion? Well, 1/2 times 1/2, or 1/2 squared, is 1/4. So the quotient of the areas is equal to the square of the scale factor. All right, so here's our conclusion. If the scale factor is represented by k, then the area of the scale drawing is k squared times the corresponding area of the original drawing. Is it necessary to find the area of each drawing to determine the ratio of areas of the scale drawing to the original drawing if the scale factor is known? Well, no. Once the scale factor of the corresponding sides is determined, the ratio of the area of the scale drawing to the original drawing is the square of the scale factor. So why is the scale factor often given as a percent or asked for as a percent, but the area relationship is calculated as a fraction? Why can't a percent be used for this calculation? Well, a scale factor given or calculated as a percent allows us to see if the scale drawing is an enlargement or a reduction of the original drawing. However, in order to use a percent in a calculation, it must be converted from an equivalent decimal or fraction form. So even though, yes, you can write it as a percent, you're probably going to end up using it anyway, so it's probably better to just keep it in a decimal or fraction form. So how is this relationship useful? Well, if none of the side lengths are provided, but instead a scale factor is provided, the relationship between the areas can be determined without needing to find the actual area of each drawing. For instance, if the scale factor and the area of the original drawing are provided, the area of the scale drawing can be determined. Similarly, if only the scale factor and the area of a scale drawing are given, the area of the original drawing can be found also without finding the side lengths. So why do you think this relationship exists? Well, if area is determined by the product of two linear measures, and each measure is changed by a scale factor of k, then it stands to reason that the area will increase by a factor of k times k, or k squared. Because remember, similarity is the fact that the side lengths are governed by a scale factor. So let's take a look at example 1. We have a big square, 5 units, and then a little square, which is 1 unit. So what percent of the area of the large square is the area of the small square? Well, again, the scale factor of the small to the large square is 1/5. Because if we're going from small to large, or I'm sorry, from large to small, then that means it's a reduction, so it has to be less than 1, so that's why it'd be 1/5. So now the area of the small square to the large square is 1/5 squared, which is 1/25, which is 4/100, or 4/100ths, or 4%. So the area of the small square is 4% of the area of the large square. All right, example 2. So what percent of the area of the large disk lies outside of the smaller disk? Now again, that means that we're going from small to large, so this is going to be an enlargement. Well, it would be twice as much, because if you figure that the radius of the small square is 2 and the radius of the large square is 4, then that would be 4/2, which is 2. So the radius of the large square is 4, the radius of the small disk is 2, or large disk and small disk, so it would be 1/2. So that way, if this is 1/2 of the larger disk, that means it is 1/2 squared, or 1/4, which is 25%. So the area outside the shaded disk is 3/4, or 75%. So why does this work? Well, the relationship between the scale factor area has already been determined. So determining the percent of the area outside the shaded region requires going a step further and subtracting the percent within the shaded region from 100%. Alright, so let's take a look at example 3. If the area of a shaded region in the larger figure is approximately 21.5 square inches, write an equation that relates the areas using a scale factor and explain what each quantity represents. Determine the area of the shaded region in the smaller scale drawing. So the scale factor of the corresponding sides would be 6 is equal to the percent times 10. Remember, 6 is the part, 10 is the whole. This is our original drawing, so that's why it is 6 is equal to percent times 10. Which means percent is equal to 6 over 10, which is 3/5, or 60%. So the area of the shaded region of the smaller figure is, the small area is equal to k squared times the large area. So that means it's going to be equal to 3/5 squared times 21.5, which is 9/25 times 21.5, which if you have your calculator, you can figure out is equal to 7 7/74. So in this equation, the square of the scale factor, 3/5 squared, multiplied by the area of the shaded region in the larger figure, which was given to us as 21.5 square inches, is equal to the area of the shaded region of the smaller figure, which is 7 7/74 square inches. So all this blue area here would measure 7 7/74 square inches. So the shaded area of the small figure is about 7 7/74 square inches. All right, example 4. So use figure 1 below in the enlarged scale drawing to justify why the area of the scale drawing is k squared times the original, or the area of the original figure. So here we have figure 1, which is width times length, and this figure 2, if it's been enlarged by a scale factor, the scale factor being k, it'd be k times the width and k times the length. So the area of figure 1 is area is equal to length times width. And the area of the scale drawing is also length times width. However, in this case, it would be, if it's length times width, the width is being represented by kw, or k times w, and the length is being represented by k times length. So therefore we get KL times KW. Well, if that is the case, then that would equal K squared times LW. Since the area of figure 1 is length times width, then the area of the scale drawing is K squared multiplied by the area of figure 1. So explain why the expressions K times L times K times W and K squared times L times W are equivalent. How do the expressions reveal different information about the situation? Well, K times L times K times W is the equivalent to K squared times LW by the associative property, which can be written as K times L times W using the commutative property. This is sometimes known as any order, any grouping. So, K times L times W is equal to K squared times L times W because K times K is also represented as K squared. So K times L times K times W shows the area as a product of each scaled dimension, while K squared times L times W shows the area as a scale factor squared times the original area, which is length times width. All right, exercise 1. This exercise reinforces the information from this lesson and the preceding 3 lessons before this. So check your answers as you go by continuing the video. All right, you should be done with the first part, which is part A. Go ahead and check your answers, pause the video, and do part B. Okay, you should be done with part B. So again, pause the video, check your answers, and then try part C. All right, you should be done with part C. Here's the answers to part C. Pause the video, check your answers, and then attempt part D. Again, remember that if you have any questions, make a note so you can bring it to class. All right, you should be done with part D. So here is the answer to part D. Go ahead and try part E. All right, you should be done with part E. So here's the answer to part E. And for part F, and part G. All right, let's wrap this up. So if you know a length in a scale drawing and its corresponding length in the original drawing, how can we determine the relationship between the areas of the drawings? Well, answers may vary, but one could be we could use the formula quantity equals percent times whole to solve for the percent. The percent is the scale factor that shows the relationship between the corresponding sides. So given a scale factor of 25%, would the quotient of the area of the scale drawing to the area of the original drawing be 1/4? Well, no, the quotient of the squares would be equal to the square of the scale factor. Therefore, the quotient of the scale drawing to the original in this example would be equal to 1/4 squared, which is 1/16. All right, see you in class.